This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So up next we have Thiparat Chotibut, who is going to talk about on the fundamental aspects of quantum extreme learning machines. And thanks a lot. Your microphone, right?
Sorry. Thank you. Thanks. Hello, test. All right. Sounds good. So I'm Thiparat from Bangkok, Thailand. I'll be presenting a joint work. Oops. The tip of the mic come out, so I'll just hold like this. Okay, so I'll be presenting a joint work in collaboration with Zoe Holmes' group at EPFL on the aspects of quantum extreme learning machines and quantum reservoir computing. I put parentheses in quantum reservoir computing because we have some preliminary results that I want to share, but the rigorous results are written in the paper on the lower right. So these concern somewhat relatively less known models for quantum machine learning, but it's getting increasingly more popular because there's no variational parameters in the quantum device. So people hope that it can avoid barren plateau. But as I'll be discussing, as you increase the expressivity of these kind of models, exponential concentration still manifest themselves in a different ways. In this case, even though the model are exactly trainable, the prediction can become ungeneralizable. So I'll start with a brief introduction to these kind of models to those of you who don't know quantum reservoir computing and quantum extreme learning machines. And then I'll be talking about how we aim for quantum advantage by looking into Fourier expressivity of these kind of models. And later on, when we don't have a perfect result, which is a typical assumption that people in the field look into these kind of models, we have short noise, and short noise can manifest themselves into an input agnostic oracle prediction of this kind of models. All right, so let me quickly introduce reservoir computing, not quantum reservoir computing yet. So in reservoir computing framework, you try to make a prediction of time series data. You have an incoming time series in high dimension, and then this time series goes into the reservoir. The reservoir can be typically recurrent neural networks, or it could be quantum system. So you can exploit this exponentially large Hilbert space to expand the feature space of this input through this nonlinear function R, and this keeps iterating forever. Then finally, you take some results, and training becomes extremely simple because you need to adjust this output weight by doing the simple linear regression to fit the output to predict a time series. And here, unlike in the variational circuits, where the trainable parameters were usually in this quantum device, here the map R, which can be recurrent neural networks or high-dimensional quantum devices, are fixed throughout. So training, in this case, is basically minimizes L2 norm. It becomes a convex optimization problems. And then you can solve exactly for this train weights in terms of pseudo-inverse of this data metrics and the feature metrics. So it's exactly trainable. For extreme learning machine is a special case of reservoir computing. Rather than predicting time series, you predict the classification of the input. So people use for quantum state estimation, for example. So in this case, I input some static picture and then want to classify whether this belongs to certain classes of the function. So training is exactly the same as the reservoir computing. You minimize this L2 norm and obtain this weight, and the prediction becomes simple in this way. And then because it's this high-dimensional mapping that people use reservoir computing or extreme learning machine as a way to represent the data, you can use quantum device as a way to encode information, and hopefully this high dimensionality of the Hilbert space enables you to get some good result. And this result representation, when applied in a simple way by obtaining linear weights, you can predict the classification quite accurately. And this has been one of the proposals that people looked into recently. So for this simple case, I'll look into the class of function f that is a scalar function rather than vector function, which could be done in general for simplicity. And the input x will be taken to be a scalar value for now. So the abstraction of this can be written down as a circuit as follows. So you have certain data encoding unitaries that input your classical data into quantum states within NA qubits, and then the whole system, accessible qubits and hidden qubits together, evolve through this reservoir UR. And eventually, assuming a perfect measurement result, you measure M observables, and this result will be used to construct the feature map to do the classification that allows you to train the model exactly. All right, so basically in our framework that we analyze, we look into the usual data encoding, unitary encoding, and then this whole system go through the reservoir evolution, and eventually some expectation results are taken. People in the field typically assume that this can be done with perfect precision, which is not the case in practice. And the prediction function that we analyze, the expressivity, is basically the linear combinations of these observables result. So the natural question is that can we look for quantum advantage in this kind of prediction, and how expressive is this? So to look into that, we first look into the expressivity of a single readout observable. You can follow Marie-Schul's paper on looking into the Fourier expressivity of these modes. You can count how many modes that can observable result represent. It turns out that the number of available Fourier modes depend on the encoding strategy that you use. If you use an encoding strategy that have the difference between eigenvalues that are exponentially many in the number of qubits, then the upper bound of it is determined exponentially in the possible value of the encoding eigenvalues. So that is something that we would like to have high expressivity. And the amplitude of these modes are controlled by the overlap between the observables and the reservoir dynamics. So all these factors come into play in terms of determining the expressivity of this kind of model. In this case, I write down I and J to be the qubit basis that correspond to computational basis that diagonalize the original encoding Hamiltonian. So natural strategy that people sometimes use is to use Pauli reuploading, and in this case the number of available frequency is only polynomial in the number of system size, which is not very good in terms of trying to push the expressivity of the model as you saw earlier. Amplitude encoding is a part of this Pauli reuploading, so we might not want to use that if you want to have quantum advantage in this kind of model. On the other hand, there's another exponential encoding strategy. Rather than encoding the data in each qubit with the same Hamiltonian, you use a specialized Hamiltonian encoding that guarantees you have exponentially many frequencies. Now, the question is, now you know the available Fourier frequencies that you have, but in fact, this amplitude might not be easily determined. It depends on the overlap between the reservoir evolution as well as the observables that you have. So the question is, like, given this kind of expression, what is the minimum number of Fourier bases that you can determine that would determine the expressivity of this kind of prediction? So you want to have as many bases as possible, right? Naturally, you can see that the number of available Fourier frequencies determine this Fourier expressivity. And secondly, it depends on the number of observable results that you take out. If you have only one observable, then this becomes just a single linear combination of many Fourier modes, and there's no way to control the parameters. So you need to have sufficiently large number of measurements as well. And eventually, it is also upper bounded by the number of observables that you take. And in this case, the worst case is you take all possible measurement for NO observables. You have 4 to the NO number of measurements you can take to reconstruct this density matrix. So it's upper bounded by this. But in practice, you only have polynomially many number of measurements. So I'll be considering only the first two competition between the number of frequencies and the number of measurements that you have. So in the case where you have more measurements than the number of available frequencies, in this case, your function is not very expressive because there's not many Fourier modes, but you have a full control over it because there are many ways you can write down this linear dependency rather than having all these Fourier modes to become linearly dependent. You have linear independence of these modes. So the expressivity of the model might not be able to take care of the function that you want to express, but you have full control over it. On the other hand, if you have exponentially many frequencies, such as using exponential encoding, then the model becomes more expressive, but the trade-off is that you have less control over free parameters. Okay. There's also another factor that determines the availability of the Fourier modes. I told you earlier that the encoding determines available Fourier frequencies, but whether or not it results in the non-zero coefficients depends on this overlap. So as you expect, if you have a highly expressive reservoir, then this overlap will be non-zero, but if your reservoir can only explore a tiny fraction of Hilbert space, then this overlap will be zero, and as a result, that will contribute to zero amplitude to those modes, and that become useless. So as we plot here is the richness of the available Fourier frequency. So even though you have encoding with exponential strategies, if you use a reservoir that is not close to high random, then your model will have less and less accessible Fourier modes. So you need a highly expressive, close to high random reservoir as well. So with the very naive, I'm not sure if some of you know this, Mudeng is like a famous hippo from Thailand, and it's really cute just to relieve some stress from all this math. So with the naive expectation, you just increase the system size and hope that you'll be able to exploit all these exponentially many Fourier frequencies. And this is true if you have a perfect readout, means that there's no short noise. And as you probably know, in variational quantum algorithm, if you have high random reservoir, the curse of dimensionality starts to kick in. And as a result, expectation values start to concentrate around certain values. So you need exponential number of shots in there to estimate these observables precisely. So in this model, it turns out that exponential concentration kicks in. So quick reminder of what exponential concentration is. So if you have an observable readout O that is supposed to depend on your input X, and this expectation will be exponentially concentrated in a system size toward an input independent value in two ways. It can be deterministic concentration or probabilistic concentration. As you increase the system size, the variance around that input independent value becomes smaller and smaller exponentially. And what does it mean if you don't have if you don't have infinite resources to sample this model? The sampling noise will come in, and then you cannot detect the distinguish between the input of X or inputs of X prime up to a certain precision. So you need exponential number of shots to estimate this quantity precisely. And this manifests themselves in baryon plateau in VQA, and in other models that is trainable also manifest themselves, for example, in quantum kernel methods that Marco worked on, and Thiparat there also worked on. And in this case, it also another manifestation of this phenomena. So there are four ways very similar to a simple curse of dimensionality that we know in quantum kernel or in VQAs. You can have extremely expressive reservoir and extremely expressive encoding, leads to concentration. You can have global measurement-induced concentration, entanglement-induced concentration, and noise-induced concentration. This is the plot of the example when, let's say, there's a concentration, the variance of the observable reads out kind of decay exponentially with the system size as you increase the expressivity of your circuit. For other cases, I'll encourage you to look into the paper because of the details. It's quite long, but the summary of this work is that with the typical assumption of perfect result that people use in quantum reservoir computing and in quantum extreme learning machine, you aim to push for high expressivity by increasing the expressivity of the encoding and the reservoir. However, if you do that naively, it turns out that it is balanced and does trade-off by the exponential concentration that you have in the observable result. So it's kind of a tug of war and trying to get the high expressivity in this kind of models and avoiding exponential concentration. So the regime would be somewhere in between that would have a good advantage. And before I end the talk, here is a preliminary result. I earlier showed the results for quantum extreme learning machine, but for quantum reservoir computing, which is the iteration of this reservoir, you also get the same concentration phenomena as well. And in this case, the concentration can arise much simpler because you can have a simple reservoir in one iteration, but because you need to iterate over many loops, even with simple reservoir, you get concentration after many iterations as well. So this is another caution for people in the field. So, and lastly, I would like to thank my wonderful collaborators. Thiparat is also here in the audience. If you want to reach out and discuss, I'll be happy to talk to. Thank you.
Thank you very much, Thiparat. Do we have maybe one or two questions?
Yes, thanks for the talk. So I'm not sure whether you are aware of, you are known like Yann LeCun's comments on classical extreme learning machines. So the actual words are not very kind, but you can Google it. Yann LeCun extreme learning machine, you can actually read it. So his central point was that classical extreme learning machines do not have a very good performance on complex data. So normally we do not treat MNIST as a complex data set because most of these MNIST digit pairs could be distinguished by one pixel value. So is it possible to show that, actually show it on more complex data sets that the quantum extreme learning machine can actually avoid this flaw of it? Thanks.
Okay, if I understand correctly, I think you're saying that Yann LeCun has some comments about the classical version, maybe not very good compared to other neural networks, right? So the question is whether the quantum version would have any benefits.
What is flaw?
Right, so as you see here, there were some kind of trade-off already in the quantum version. We might want to have high expressivity, which we can certainly have if we have perfect result. You can exponentially many frequencies, so classification can perform on very complicated functions. But because of this trade-off, you cannot have the quantum advantage by having exponentially many frequencies. So one way is possibly to do this kind of things on the quantum data, rather than encoding classical data into quantum and think about these models as doing something like quantum state tomography, for example, that could be useful.
Yeah, okay, thanks.
So let's thank Thiparat again.